Hey guys, welcome in. Obviously I'm not here again today. I apologize for that. I'm at another training, and so I made this video here to go along with the notes for the lesson for today. The good thing is it kind of overlaps what we've been dealing with in terms of looking at our slope and y-intercept and looking at slope-intercept form, how we can graph equations, write equations, solve them, right? But we want to interpret what it means to be a specific slope in a situation, what the specific values represent when you're looking at your y-intercept and those things. So make sure you're following along with your notes here today as you go through and answer these questions as we go. And then you can use that to help you get to the point where you're ready to do your practice problems for today. So make sure you grab a copy of that from the substitute as well. All right, so what they want us to do first here in this bell work to start with our notes here, next page in our notes, is to write a slope-intercept equation from one point in the slope. So remember, we're thinking y equals mx plus b, right? And in this case, we know the slope, we know the m value, okay? We have an x and y that we can plug in here for x and plug in for y. So what we're really solving for is the intercept part of this, and then we can rewrite our final answer in that slope-intercept form. So if I plug in everything I know, my y value is -2, so I'm going to say -2 is equal to, right, that's my y value, slope -3 times my x value, which is 4 in this case, and then all of that is going to be plus my y-intercept. So I'm actually solving again for the y-intercept step. That's what I'm solving for. So I come over here and I do this step right here, the multiplication, because I know I can do that. So I get -2 is equal to -12 plus b, right? And then what I want to move to get b by itself is this -12. So I'm going to add 12 to both sides. And when I do that, I get 10 is equal to b. So I'm not quite done yet. That's going to be my y-intercept at 0, +10. So when I go back and I rewrite this, my final answer in slope-intercept form of an equation, it's going to be y is equal to the slope that I had, -3x, so whatever my x and y, -3 times x, and then plus that y-intercept we just solved for, which is 10. So if I were to graph this and wanted to find some points, my x and y coordinates, I'd start at 0, 10, 0, 10, and then I'm going down 3 over 1, down 3 over 1 each time that I do that, okay? The other part of this one said to solve for y, so we're looking over here, we're rewriting that equation. So I'm going to get rid of the parts without y first. I'm adding 8x, so I'm going to subtract 8x from both sides. And remember, I can't combine terms that are not like terms, so I'm going to have 6y is equal to a -8x and then a -14. Those two terms are not like terms, this and this, so I can't do that. My final step then would be to divide by 6, okay? And I'm dividing everything by 6, so it gets a little tricky here. I'm going to get y equals -8 over 6x, right? And then minus 14 over 6. So I'm not going to have whole numbers, right? So I could keep it like this, or if I wanted to simplify it, I could even say y is equal to, if I divide both these by 2, -4/3 x, right? And then I could simplify both these by 2 and say -7/3. We could do it that way, okay? Or if you want to write those as whole numbers or mixed numbers, you could. But again, improper fractions are nice, especially when we're dealing with slope and rate of change. We like to think vertical over horizontal, right, with our change, so you can keep it like that as you move through. All right, so let's really take a look in, and today we're really just about thinking about how slope, changes in slope and changes in our y-intercept affect our overall function, our overall relationship that's happening here with our x and y values, what that represents, and what that means. So if we think about changes in slope, a change in the slope of a function affects its rate of change. And let me make my pen a little bit smaller here so we can do this. It affects its rate of change, right? We've talked about how the change in your y values, or vertically, over the change in your horizontal values, your x values, can show that slope, or that rate of change. So changing the slope of a function is really just changing that rate of change in this situation, or in this scenario, okay? If the slope is increased, the values of the function will change more rapidly, okay? And I don't want you to be confused here, right? If the slope is increased, whether it's a negative slope that's increasing, getting more negative, right, or a positive slope that's increasing, we see more of a rapid change. We get a steeper line, right? We've talked about that with the graphs and the way they look, okay? So we see a more rapid change that happens when your slope is increased overall, whether it's becoming a bigger negative number going down from left to right, or a bigger positive number going up from left to right, okay? If the slope is decreased, then the opposite of that, right, then the values of the function will change more slowly, all right? They're not as rapid, right? Up 1 over 6 is different than going up 6 over 1 kind of thing, right? So if the slope is decreased, whether we're negative or positive, again, you're going to see the values of the function changing more slowly. They're not going to be as rapid of movements, okay? And it's a flatter line, right, when we graph it, if the slope is decreased, okay? If we think about the y-intercept specifically, all right, a change in the y-intercept will change the overall value of the function, okay? And the reason for that is because if I don't start at 0, 0, say I start at 0, 60 in this situation, right? That's going to be a lot different if I have a slope of 3. If I start at 0, 60, right? My next point would be at 63. But if I start at 0, 0, my first point would be at just 3, right? So the overall value of the function is changed when you look at your y-intercept changing. So again, thinking proportional, non-proportional relationships, where that ends up, all right? Some things to remember here. The y-intercept is the output value, or your y value, if you want to think of it that way, right? When the input, or your x value, is 0, right? So when my x is 0, the y-intercept is my output value, or my y value at that point. So 0, 10, 0, negative 3, depending on where we're at, that kind of thing. The y-intercept is always that output, or that y value of the function, when your input value, when your x value is 0. And then changing the y-intercept is going to shift, okay? Shifts the entire function up or down, right? On the graph, on the line. So if we think about that, it's shifting that entire function up or down in terms of its overall value, in terms of its positioning on the graph when we create that. And so that's something that we need to think about as well. So these are all some things we've talked about and touched on a little bit, but it's also good reminders here as we get ready to do some of the practice with this type of interpretation day. All right, so we're going to take a look at a few of these examples. We might not go through all of them today because I do want to give you guys time probably to do some practice problems as well on your assignment. But we're going to take a look at a few of these and just kind of understand and talk about what they mean. So in this example, we've got Sam is a bicycle courier, so he's carrying things or delivering things on his bike. Or she earns $10 for each delivery plus 75 cents, okay, for each ounce the package she delivers weighs. So the graph of her pay is shown below. So we start at 0, 10, right? This is a point 10. So at 0, 10, so she's earning 10 for each delivery, but then it's an extra 75 cents, right? An extra 75 cents for each thing that she delivers in terms of the number of ounces. All right, so the graph of her pay is shown. So what would it mean if the slope of the graph were doubled? Okay, so my slope is the thing that's changing. 10 is not what changes. That's the given, the flat rate, right? What's changing here is the 75 cents. So if we went from 75 cents and doubled it, right, take that times 2, that would be $1.50. So what does that mean in this case, right? If we were doubled, she would make twice as much per ounce is what's happening there, right? Per OZ, ounce, right? Making twice as much per ounce, which would definitely help, right? You're going to get twice as much per ounce for that weight, and so that would be something that's really good. It said, what would it mean if the slope of the function were changed to 0? If they were changed to 0, if the slope were 0, she would not be paid for the weight, right? For the weight of, make this a little bit bigger, for the weight of the package. Sorry about the bell. Okay, if the slope were 0, right, there's no rate of change happening here. If it was just a flat line, that means she would just get $10 for delivery, right? But again, that's probably not fair in this situation. We wouldn't want that to happen. That definitely is something we wouldn't want to see, right? So then 1b, the question 1b says, what would it mean if the slope of the function were negative? Well, if it was negative, that means that she would be owing money, right? Or losing money, owing or losing money for the weight of the package. And that probably doesn't make sense here either here, right? Weight of package. Okay, if it was going down, right, she'd be losing that money for the weight of the package. So again, that doesn't really make sense for the scenario. So looking at 3 different pieces here, right? If we doubled it, what would that mean? If it were 0, what would that mean? And if it were negative? And really, you know, these last 2 aren't really fair in this situation. They don't make a whole lot of sense, right? We wouldn't want to probably not pay them at all for extra weight, right? It takes a little extra effort to do that kind of thing. We're definitely not going to have them owing or losing money if the weight of the packages were going up. So 1A and 1B really don't make sense in this situation. So again, interpreting the slope and understanding what it means in this situation is really important based on the graph where we start here and this what that means overall in terms of our value. All right, so in this one, we're looking at Melinda here, and Melinda is driving home at the speed of 80 kilometers per hour, okay? Her distance from home, that's the big thing right here, is shown on the graph, right? That's why we have a negative slope, because she starts at a certain distance. So at 0 hours, right, or at 0 time, 0 hours spent driving, she's 400 miles from home. But then as we go over time, right, it looks like we get to the point where it's at 5, because I think these each go up by 1, it looks like on my x-axis. By the time she gets to 5 hours, right, which makes sense if she's going 80 kilometers per hour, 5 hours she would make it all the way back home. Her distance would be 0. Okay, so it says, what would it mean if the y-intercept of the graph were increased by 40? That means she would start 440 miles from home instead of the 400 that it is right now. Okay, so if the graph were up another 40, she would be 440 miles from home instead of just 400, right? If that's where it was increased by 40, it would go up that much, right? And so that would change her overall time too. If she goes 80 per hour, it would change her overall time it would take to get her home. It says, if the y-intercept were halved, how would the total amount of time it takes Melinda to get home be affected? Well, if I cut that in half, right, if it's 200, right, if it's 200 miles from home, right, and she's going 80 kilometers per hour, so 80 kilometers per hour, right? How would that change her overall distance, or sorry, her overall time that it would take to get home? Well, right now, if it's 400, it takes her 5 hours to get home, right? So if I cut the mileage in half, right, the y-intercept, if I start at 200, if I do 200 divided by the 80 that I'm looking for here, how would that change my overall measurement? So let's think about that and pull it up really quick here. So if I take this and I do 200, right, divided by the 80 per hour, right, it would cut it in half and make it 2.5 hours, right, for her to get home, which makes sense, right? If I cut the distance in half and I'm still going the same speed, I'm still going 80 kilometers per hour, that means that I would cut the time in half as well. So again, changes in the y-intercept, what that means. If it starts at 440 miles from home, that would make the overall travel time spent driving longer. But if we cut it in half, we make it smaller, shorter, right? If we decrease it, make it only 200 miles, that would also cut the drive time in half because we're still going the same speed. Now let's take a look at a couple more here. We'll do Gwyneth and then we'll pick one more from the next set to do here really quick. But if we look at Gwyneth, she's talking about a school fundraiser benefiting the organization treating diabetes patients. For each student that participates in the fundraiser, the school donates $10. So that's where we're starting here, right? It says contribution per student. So they're going to get 10 no matter what, right? Each student's going to get $10 from the school. So that is already, before you even get any donors, any people that are pledging money for your name, through your name, you have $10. In addition, the students obtain a pledge of $7 each day from the donor that they find. The graph is Gwyneth's contribution in terms of the number of donors she finds, and that's shown below. So if I look at this, and I was trying to even write the equation because we haven't really talked about this too much so far, this would be what it looks like here, right? The $10 that you start with plus the 7 times the number of donors, that's what my x value represents, is going to equal my total contribution, my y value here as we go through this. So if I think about it, the slope is 7 because that's the rate of change. My y-intercept is 10. I'm starting with $10. So each donor is going to go up by $7 from there. So it says, if the contribution for each donor were increased to $9, how would the graph change? Well, my slope would now be 9, right? And so that means that I would start at 0.10 and go up $9 each time. Up $9 each donor, right? So it would change my slope. It wouldn't change where I start my graph, but my slope would be a little bit steeper. My graph would go up quicker because I'm making, right? I'm making more money per person that donates, which is $2 more than what I did before, right? So the slope of the line would increase, causing the line to rise more steeply. Yes, that fits here, okay? If you think about this one, the line would cross the y-axis at 0.9 rather than 0.10. That's not the right answer because that's not what's changing here. The rate of change, or my slope, is what's changing. So the line would cross the x-axis at 9.0. That's not true either, right? If it was 9.0, that would mean I'd have 9 donors, right? And $0. Not a chance. We're making more money as we go up. The slope would decrease, causing the line to be rise less steeply. Nope, not a chance. So A is our best option here based on what's looking at, right, and how we would answer that question. So let's skip ahead to this one with the phone company, because this is a good one just kind of as an example. So I know we're going to not do every single one that's in your notes. If you want to go back and look at some of those, you can, but you're going to have plenty of practice problems too, guys, that look a lot like this. So let's look at this one in particular because it's a good just example of how things have changed over time here. Because now a lot of companies won't have plans like this, and even if they do, right, most people don't accept them for this reason. So it says a phone company is going to charge you $30 per month, and then plus 10 cents for every minute of long distance phone calls, right? Crazy to think, right? And maybe this is like, oh, 10 cents, not a big deal. But if you think about it, if you called somebody, like you have relatives, family members, other friends, that kind of thing, long distance means outside of kind of Kansas City area, this would add up over time, right? 10 cents for every minute would be, you know, a lot, right? So let's think about that. It's like $1 for 10 minutes, that kind of thing. So if I look at this, right, my Y values, the money that's charged here or monthly charge overall, and my X is that long distance call in minutes. So if I were to write an equation to represent this, it would be Y, my monthly charge, that total is equal to the 10 cents, so 0.10, we can just do 10 cents, times X, the number of minutes for that long distance call, plus 30, because we're starting at $30 for that monthly charge. So it says, which of the following would increase the charge per long distance minute to 20 cents, right? So what would that be? Well, if I'm looking at the change per long distance call, I'm looking at a change in my rate of change, or my overall value that I'm looking at in terms of time per minute, right? So I would be looking to make this 20 cents. And if I focus on that, right, that part of the equation, that is my slope. That's what I'm thinking, right? So having the y-intercept, not a chance. Having the y-intercept just means I would be at $15 to start. So that's not what's happening here. Okay, doubling the y-intercept would be up here at 60, right? 30, 35, 40, 45, 50. So it'd be like up here even somewhere off the graph, right? That's not what's happening, all right? I'm not having the slope, because if I have the slope, that would be taking this and making it only 5 cents per call, which we would really like, right? Anytime you can lower the price, that'd be good. So that's not what's happening here. I'm actually doubling the slope, or doubling the rate of change, right? In this example, right? I'm making that twice as much as what it was right here. And so D is my answer because I'm doubling that slope and coming up with my answer. All right. So again, just some things to think about as you work through some of these examples. And again, I'm not going through all of them with you guys here because you can go back and look at some of the extra ones you need to. But I think hopefully with the examples we've done, you can kind of see what the expectation is in terms of interpreting what your slope and y-intercept mean in a scenario. So if you jump ahead to these last few pieces from your notes today, just some good things to consider and to think about, and what that means in terms of how these functions are related and showing different things. So these last few slides are just some descriptors here to help you when you think about what's happening or occurring in these situations. So the first thing says, you know, when you think about graphs of functions, linear relationships like these are, the graph of a function can be either continuous or discrete, okay? So we use these terms, these are math terms in terms of looking at data and overall values statistically with our function. So continuous functions is if the graph of a continuous function, the points are connected with a continuous line. Okay, so we've seen a lot of those so far, right? This is because every point on the line has meaning based on the original problem. So if you see a continuous function, that's one that is connected, right? The points are connected. It's fluid, it's continuous, goes on forever and ever, that kind of thing. If it's a discrete function, right, they are separate, distinct points. Separate and distinct points. So that's something to think about too as well. When you come to see some of these examples, right? If they're not connected, right? They're not connected by a line. That's because only the points have meaning. There's nothing in between those values, okay? The points that are plotted, the points between the plotted points cannot be interpreted based on the original situation. So that's why they're not connected, why it represents a discrete function. So thinking about that and going a little bit further with this too, if I can get to my next slide, there we go. An example of a continuous function here, right, is something like this. This graph is continuous because the temperature was steadily rising, including between measurements, right? So we're not just focused in on 10 o'clock, right? There's time in between 10 and 11, and it's steadily increasing at that rate. So at 10:30, the temperature might have been right around 3 degrees if we kind of follow this line, because it looks like in an hour it's going up by almost 2 degrees each time, right? As we continue to look at this. So at 10:30, halfway there, right? Halfway between 10 and 11 would also be halfway between 2 and 4 in terms of temperature. So that's a continuous line that I could, or a point that I could put on that continuous function line. If it's a discrete function, right? So an example here, a discrete function would be something like this. So if we're thinking number of tickets purchased for maybe a school dance, something like that, right? And I'm looking at total cost, right? I'm not going to sell part of a ticket, right? I'm not going to give you like 1 and 2/4 of a ticket. And that way I'm not going to also get a total cost that's in between these values. So a discrete function here represents this situation because we had a set number of tickets purchased, right? And then just one set value. There's nothing in between. It's not a continuous. If there's one ticket purchased, we're at 10, 220, 330, right? 440 and 550, right? So that's a discrete function because there is no in between, right? There's nothing connected here. And that's why there's no line between those two. All right. So if you guys think about that and just think about some of those examples that we've done, it's just important to see how that changes, right? How that's a little bit different. So our linear functions have been continuous examples. That's what we've been looking at when answering that. Okay. So here's what I'd like you guys to do and like you to understand. All right. You're going to get your practice worksheet from the substitute teacher. I only want you to do questions 1 through 10. Okay. So we're talking about the first 2 pages of this packet. We'll get to the rest of them tomorrow and over the weekend, but 1 through 10. So when you guys get this and look at it, right, when you have this here, 1 through 10. So the first page, front and back, and then the second page, front and back. So you get up to question 10. So you're going to finish with the one where it says Nan is working as a commissioned sales rep. So at 10, you'll finish there. There are a couple other pages in there with some different types of problems, and we'll talk about those tomorrow in class, and then through the weekend you can work on them, that kind of thing. So I'm just asking you guys when you get this worksheet to get through 1 through 10 from the substitute. All right, so make sure you watch this video. If you have questions after you take the notes and go through them, make sure you have them ready to go at the beginning of class tomorrow, because I will be back in class on Friday morning. All right, shoot me an email if something else comes up throughout the day, that kind of thing. Otherwise, I will see you guys in class tomorrow, and thanks for working hard today while I'm gone.